Okay, so let's test our code. If name equals main. Alright, so tree equals AVL tree. Tree dot insert. As you can see, we are only getting two methods, insert and traverse. So actually this was my aim to this was the real reason why I made all the other methods as internal methods, or we can say strongly private methods, right? So this is how we demonstrate to keep the implementation, kind of a secret. So we wanna hide that implementation from the user. Okay, so tree dot insert. So let us insert 12. Insert 24. Tree dot insert 10. Tree dot insert 0. Tree dot insert -2. Insert 20. Tree dot insert 21. This time. Tree dot insert 19. Insert -6. -3. Tree dot insert -10. Okay, so I think that's enough. Tree dot traverse. Okay, so it should work. I hope. Oh well, I think we are not getting all the items in our list. So I think there is an error, or maybe I missed something. It is working fine, but it is not printing all the other variables. Sorry, all the other data which we have inserted. So I think all the methods seem to be fine. Let's check the insert first. So the first method is fine. Oh, okay. So I forgot to write the else block or in this section of this method. And okay. So I think I have to do some include this here. Else uh, node dot write equals node data, and node is the parent, right? So this was the line which I forgot. So let's run the code again. Yeah. So as you all can see, all the data has been printed in an increasing order. So first, and here you can see that the code has made rotations on these nodes 10, 20, 24, 6, -2, 0. So 10, -6, 3, -2, 0, and all the way down 10, 12, 19, 20, 21, 24. So the insert method and rotation methods are working fine. Now we have to make the remove method. All right. So this remove method is exactly the same as that of a binary search tree, right? So, so I have two options that I can just copy paste from the binary search tree, or just create another method from scratch again. So I'll go and I'll just make the function again just for my own practice, and so that you all can follow along. So remove. Okay, so this method is a bit lengthy. So we remove data. Okay. Now, if not self dot root. First, I am checking that if there is no root, Then I want my code to print no data, right? Now else means if the root exists, then we are going to call another method. This is going to be remove data. Just the way we did for the insert data, right? Insert method. So this is what we are going to do. So remove data, and another argument is going to be self.root. So we are telling this remove data method that here take data and take the node, start traversing from this node, find the data and remove it. Alright. So okay, so let's create the internal private method just after the insert data method. Right. So define remove, write this, data and node. Right. So first we have to look for the data. First we have to find the data. So how are we going to find the data? So again, the if statements. If data is smaller than node dot data, then if there is a node dot left, then call the method again, and this time we are going to pass data and node dot left. Right. So I hope I am clear so far. Like we are finding data, comparing it with the current node's data. If it is small, then we are telling the code to call yourself uh, recursively and check the left subtree. Alright. So now elif data is greater than node dot data. If node dot write self dot again remove data, this time data and node dot write. Okay. Now the third condition is going to be elif when we find the data. Okay, so if data is equals to nodes data, now this is where we have successfully found the node which contains our desired or target data, right? So now we have to check for various conditions. The first condition is when the node to be removed has no child. So there is no left child, there is no right child. It means it's a leaf node. Okay, so we call it as a leaf node, right? So if not node dot left and node dot right. So this is our if statement which is checking if not node dot left and not, I forgot to write the not here. Okay, and not node dot right, which means node dot left is a none and node dot right is also a null. Now first we are going to create a parent node. It's going to be node dot parent. Now there are going to be two conditions. They are going to be similar to what we did in our rotation methods. Okay, first we are checking if parent node exists. All right, then if parent node dot left was the node to be removed, then parent node dot left now will point towards a none. Why? Because there were no children of our current node which is to be removed. Okay, it means the node points to a null, right? So obviously if we are going to remove the node, the parent node is now pointing towards the none, right? So similarly, elif parent node dot write equals to node, which means if the parent node's write node was the node itself, then we are updating the parent dot write as none again. Now else, now why else? If it is a root node, all right, and root node has no parent, so I think I should just add a comment. If the node is the root node, okay, so if it's the root node, then self dot root is going to be a none. I think this is clear to you all. Now, as we don't have any children, we don't need to update the child to parent relationship, right? So we only need to update the child to parent relationship when a child exists, and here the child does not exist, right? So simply we are going to delete the node, and we are going to call the violation handler to the parent node. Okay, so well, we don't actually need to include this method, because why would we want to handle the violation if the root node is settled? But still we have to include this so that the violation handler starts from the current parent node and checks the violation all the way back to the root node. Right? Okay. Now, second condition. Okay, so second condition is when the left child exists. Okay, so if uh, node dot left and not node dot right. So when the node dot left exists and the node dot right does not exist, okay, so we are going to do the same thing. Parent node dot parent. So if parent node, now if parent node dot left was the node which we want to remove, okay, so if it was a node, now we are updating the left node of the parent node that it has to point towards node dot left, because this is the way we balance, keep the tree balanced. And if we are removing the node, we have to attach the node's child, whatever child it may be, left or right child, to the parent node, right? So I'm including a small comment. This is parent to child relationship, okay, and similarly else elif, sorry, parent node dot right equals to a node which we want to remove. So parent node dot right is going to be node dot left again. So now else part, if there is no node, so self no parent, sorry, so if there is no parent, self dot root is going to be node dot left, right? Because the node which we have to remove was the root node. So obviously, if we are removing the root node, we have to attach the child of the root node. So the root node, the new root node is this node dot left. Okay. Now this time we do have the children nodes, right? So we have to maintain the child to parent relationship. Okay. How are we going to do that? So node dot left dot parent equals to parent node. So originally the node's parent was node, right? Node dot left, right? Node dot left is enough for us to understand that node is the parent. Now we are updating the parent parameter as parent node. So child knows who is his parents, right? So now we are going to delete the node. Oh, sorry. And finally, self dot violation handler parent node. So this method is going to start checking the violation and setting the hides which we have already made. You know, this is the violation handler method. So this is going to update the hide, then it's going to call the fixed method, and then it's going to update the variables all the way up to the root node. Okay. Now another condition, third condition, when write child exists. Okay. So if node dot right and not node dot left, so this is going to be the same, and I think I should just copy paste here and make changes this time. So copy, paste. Right. Now we have to check. We have to make some changes. This time node dot right, again right, right, and I think we're done. So let me just have a look again. Parent node is node dot parent. If parent node, updating it to the, we are updating the parents left here to the nodes right, and we are updating the parents right to the nodes right. Okay, fine. Root is updated to node dot right and node dot left dot parent. Okay, so here node dot right dot parent is going to be the parent node. We deleted the node and violation handler. Okay, so now the last condition, the fourth condition, when the node has two children. So what we have to do is A, we have to find the find either the predecessor node or the successor node. Then swap the values of the node and either of the above mentioned nodes, right? The predecessor and successor nodes. And then C, delete the predecessor or the successor. Okay, so this is what we have to do. These are the steps. So first step, we have to use the if statement. So if node dot left and node dot right. Now let us go for the successor node this time, and it's going to be self dot, again a different method, find successor. Okay, and for the successor node, for the successor node wait the successor node is uh, the smallest node in the right subtree of the node. Okay, so node dot right is what we are going to pass in this method, node dot right. Okay. So it's going to be the next node to the uh, current node. All right, now successor node and successor node dot data and node dot data equals node dot data successor node dot data. So this is where we are swapping the two values. Now self dot remove successor node dot data from the tree node dot write. Okay. Now let us create our method. Define find successor and node. Now if node dot left return self dot find successor node dot left, else return node dot data. So this is how we are recursively reaching out to the leftmost node in the left subtree of our node, right? And don't forget to use the return statement, otherwise successor node will contain only a null value, right? So this is, I think this is it for our remove method in an AVL tree. Okay. Okay. So let us check our code and let's remove any random number. Let's remove 12 and see if 12 has been removed or not. Okay. So there is some error. Int object has no attribute data. In this line. Oh, sorry. We did something wrong here. We don't have to return the the value. We are actually wanting to return the node itself, right? And here we are using the data attribute. So now I think it should work. Okay, again error, local variable node reference before assignment. Okay, so elif, we have to use the elif statement. Yeah, so I think it's done. Yeah, here also we have to use the elif statement, right? It should work now. So yeah, 12 has been removed. Let us remove some more items. Tree dot remove 10. Tree dot remove -2 this time. Tree dot remove 19. So we are removing 4 items. 10, 12, -2, 19. So I think the nodes have been removed. 10 is gone. So we remaining items are 1, 2, 3, 4, 5, 6, 7. And we inserted how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So this is it. Our code is working fine. So in my next video, we are going to make the find method, minimum and maximum method. So see you there.